Play. So we're actually going to have a lecture today, or at least the first little bit is going to be a lecture, first 30 minutes or so. So we're going to start talking actual stats. Obviously, you guys have been learning R, but that's been mostly learning R as a tool for looking at and manipulating data. But now we want to actually talk about drawing inferences from data. So a little bit of sort of roundtable discussion. So why do we do experiments? Like as people doing science, why? What are we trying to achieve when we do experiments?
A lot of stuff.
Okay. So for example, like what?
Trying to figure out your hypothesis, whether it's true or not.
Okay.
You have a hypothesis.
Okay.
And you're trying to solve that again.
Yeah.
Well, I look at it in small sections, like some people are more interested in improving the process of investigation and disease detection with a better, more efficient, cost-effective way.
Okay.
Some others would look for new therapeutic intervention. Again, it should be cost-effective and improve quality of life. And like there's still a lot of stuff unknown in medicine that we need to figure out what's going on.
Yeah. And how would we answer those questions? Like how does an experiment answer those questions?
Well, some experiment we are introducing an intervention. So we are comparing the gold standard with whatever we're proposing as our hypothesis, saying this way it's shorter and less costly. So we compare these two pathways and we'll see which one is better and can we replace this with that.
Okay. Any other thoughts?
Share some experience.
Yeah.
I've been working with the cancer field for a long time, and we noticed that it was in the Middle East, especially in Dubai and this stuff. We were experiencing some differences in the response of local patients versus the international patients, for example, for any new cancer medication.
Yeah.
So we thought about there could be some sort of ethnicity or something, or a group of people could respond differently because of gene mutation or whatever. So we were following the FDA, for example, for the United States to apply the new indication in the country.
Yeah.
But we do the similar that has been done there for our group of people and to make the comparison.
Right.
So to be able to answer this question, the comparison should be fair enough and significant enough. And we need to go for example to calculate how much the sample size we need to reach like a significant difference versus the original publication. For example.
Okay.
So usually work with the statisticians to ask them. We'll give them like the end point of the trial, the clinical research.
Yeah.
And they tell us, okay, if you want to reach this end point with this significant number, you need to start with this sample size.
Right.
But what's in between, I don't know.
Okay.
I'm here to know.
All right.
This
So
is my experience.
Yeah. So we've got a couple answers that sort of have fairly detailed perspectives on specifically health science and how we do that. I mean, a little bit more generally, like what is like what are we trying to do across different types of science and across different
To have a result that we can use in the future.
to have a result we can use. Okay, so and another way of talking about hypothesis is to that I will often use as model. It's just sort of model tends to connote a more sort of thought out mathematically thing, a story for how data came about. Hypothesis can be used interchangeably. You'll often hear me talking about models because we will be having mathematically sort of defined hypotheses when we're talking here. But when we go into an experiment in theory with some sort of question about the world, and what are we trying to what are we trying to do? So you said determine if our hypothesis is true or not, and we had and what was your nuance on it? Oh no. Well, she had to test the hypothesis. Okay, that's kind of like saying, or a little bit more vague version of whether it's true or not.
I think the end result is to produce knowledge and science.
Okay, that's a good answer. Produce knowledge. So we want to gain information about the world. Um,
You said an experiment using a small sample to gain your whatever like hypothesis or what you're thinking is, and then you reflect it to the whole generation of the knowledge or like rules.
okay,
So
not
you set experiment from a small group of like sample, then you gain the knowledge.
ah.
Of the whole.
Right. Okay. So you sort of, by doing an experiment on, say, a subset of people, you can gain knowledge that may generalize to everybody. So, in the case of medical practice, that may allow you to change the way you treat the whole population on the basis of how you've observed the single population. Okay. So I just wanted to start us thinking about that. Now, how many of you have? I was taking an undergraduate statistics course part of the requirements of the no. Well, of the degree, no. And it certainly wasn't of this course. Um, so, for those that have had some exposure to statistics in the past, does anybody remember what a p-value is? Okay, so let's. For those that know, what is a p-value? What can you remember what it means? So.
It's like it's representing the significance difference between two factors, and this is my understanding. And for example, if an experiment or a question for an experiment has been done 100 times, has been repeated 100 times, it should give the answer at 95 times at least. This means this is significant, and you have 5% error or 5 times error. That is my interpretation.
Okay.
I'm not sure.
Yeah, that's one common interpretation.
In generic terms, I think p-value helps us to understand if our experiment is valid. Basically, we set p-value on a specific number, like 0.5.
Yep.
And anything below 0.5, let's say from 0.01 to 0.5, would make that experiment valid.
Okay.
Anything above could make it insignificant.
Mm-hmm. Okay. So we started out when we were talking about experiments, we had the idea whether the hypothesis is true or not. It turns out that, well, just because there's so much noise in the world, and particularly when we're only observing, say, a sample of a greater population, we can't ever really say for sure from a specific result what's true or not. So this is, we take the perspective here that maybe the p-value is something that says about whether our test has come out one way or the other. And okay, any other ideas what a p-value is?
Could be how much I can expand my results or what I infer about my sample to the general population.
Okay, so that's kind of related to this idea of validity, like can it generalize? Any other ideas?
I think, as far as I remember, it shows the percentage of the chance that the result may be against the result that you have reached. I mean, the probability of reaching that result by chance.
Okay, so
It's 95% time. 95% of the time, you will have this result.
Mhm.
That's what it's explaining. It's the probability of having the same result or better if the null hypothesis is true.
Okay, so I think there's a slight nuance between those two explanations. So yours sounded a little bit more like his, talking about 95% of the time, if you were to repeat this, you'd get that same result.
That's confidence interval.
Aha.
Yeah, it's almost confusing.
Yes, yes, yep. And that's entirely
But I have said
entirely common that confidence intervals and p-values get a little confused. They do have slightly different interpretations, even though the math going into them, the numbers are actually the same. Back here we had the idea, though, that it's the probability, I think you said it's the probability that the result we obtained is due to chance. Okay, we have an idea back here, or was that it?
Similar to what you say, it's like critical value that is set aside that we compare our result with to determine whether our conclusion is significant or not.
Okay, so that somewhat relates to the idea that you propounded that you kind of set a criterion at the outset, and that sort of dichotomizes the result into either sort of we're going to decide the hypothesis is true or decide that it's not true. Any other perspectives or understandings?
It is most probably a probability of something happen by chance in a small group and compared to like, and there's a like value for the group, large group, right?
Yeah.
So like we are getting something like randomly, like because of, by chance we are getting something, that is the probability. There's a value like mean or something for the population. So that value we are getting some values
Yeah.
by the chance.
Yeah.
That's the p-value.
Okay. I want to say that I think the way I understand you, I think so far you're the closest. This is a problem with traditional statistics, is that we have very different understandings in this room of what this thing is that pretty much consists of most of the statistics that you've talked about. Whenever you read papers, really all you look at is the p-value. Oh, less than 0.05, or if it's got lots of zeros in it and then a number, that sort of is what you look at. But so far, everybody so far is wrong. And it's not your fault. I'm going to talk about why it's not your fault, that the traditional perspective that you've been taught is not only a incredibly confusing concept and too confusing for most people to really encode, but it's also not very useful. So quick quiz. You guys are going into health. So in a clinical trial of a particular test of cancer, the test was found to be 80% accurate in identifying individuals with cancer and 70% accurate in giving those without cancer a clean bill of health. If I have a patient that comes to me with a positive test result, what is the probability that they have cancer?
So can you explain the patient?
Okay, so you're a doctor. You have a patient coming to you. You use a test on this patient, say it's a blood test or something like that, and you know that it's, for those people that have the cancer, it's 80% accurate at saying they have the cancer. For those people that don't have cancer, it's 70% accurate at saying they don't have cancer. So yes, yeah. So we have a question over here.
Well, sort of. Yeah. But go on.
Well, I was going to say, so the person comes to you with the positive test, and they ask you, what are the chances that, like, I have cancer?
Well, according to this, they're saying that 80% of the people who are given positive are true positives, and 30% of people who are given a false negative.
Well, the way it's worded, it's 80% accurate. So typically when you do a clinical trial of there's some gold standard test of cancer. So it says 80% accurate in identifying individuals with cancer. So of the people with cancer, it's able to tag them as you have cancer 80% of the time. You can think of that as 20% of the time it misses cancer. So, and then the other ones, it's 70% accurate at giving those without cancer a clean bill of health. So again, you have people that you know don't have cancer, and 70% of the time it says, no, you don't have cancer. But 30% of the time it gives them a false negative saying, yes, you do have cancer. So you've got something where it's got 20% of the time false negative and 30% of the time false positive. So
if someone has a positive test, then it's 80% true.
What does everybody else think? I think so. I actually, the different terminology is used in the different fields.
No, it is not. True positive plus true negative divided by the total number of the patients. I guess I'm not sure. I guess that's the equation.
Sorry, what's on the bottom? Divided by?
So true positive, false positive, true negative, false negative. So 80, 20, 70, 30. And when the equation is 80, 70 plus 70 divided by.
All right, so
I'm not sure
we,
which is-
some of you have big calculators in front of you in the form of computers. What do you want to work that out?
60 or 40.
Maybe even just ballpark it. What do you think that would come out as? If you were standing there as the physician and you had those two numbers and somebody with a positive test, what would you feel is there? More than 50? Okay, who thinks it's more than 50% chance? Raise your hand. Okay, about half of, or a little bit more than half of you. Who thinks it's less than 50%? Who thinks it's more than 70%? Nobody. Who thinks it's less than 30%? Two people. Okay. Who thinks that you can't answer the question yet? Okay, we got a 3. Do you know why you can't answer the question yet?
You don't have the exact number for the whole patient.
You don't have the exact number of all the people that were involved in the trial. No, that's not the number that you'd need.
The type of patient. What kind of patient you have done the test or like clinical trials?
Okay.
To whom it has been done and these values are gathered from the part of like the population, the subset of population.
Okay, let's say you had sort of in this clinical trial, you had a representative sample, so it matched the characteristics of the population you're trying to. Do you think you'd still, if having that information, do you think you have enough information now?
I'd say the percentage of the false positive and negative is too high, so it's not a super accurate.
Okay, that's one. So is that? So that makes you just uncertain as to. It's not specific.
I think that we're missing like a method or a calculation way to calculate this, and it could be like you need another confirmatory test.
Okay, you want to have another test, say a repeat of the same one, or okay. Oh no, just another more gold standard test that you use. That sort of is along the lines of asserting that this test isn't very good in the first place. That's it. All right. So key piece of information that's missing that, I mean, again, you're close here in terms of asking about what is the population characteristics. I gave you two pieces of information. The, I guess, true positive rate and the true negative rate, or alternatively, you could say the false negative and false positive rates. But in order to talk about what the probability of a person in front of you has, you need to have an extra piece of information, which is, what is the rate of the disease in the population in the first place? And this is somewhat, this seems sort of a weird, sort of in the clinic question, but this actually bears on the foundations of Bayesian data analysis. Because you can think of this, what is the general rate of things happening in the population, as your sort of the prior information. Before you even saw that person with their test, if you were to randomly grab a person in the population, what would your guess be for the likelihood that they have that disease? And you'd want this piece of information to make that guess. So that's indeed what that piece of information means. It's sort of, if you were to grab a random person from the population, they'd have a 10% chance of having the disease. So that's what's called your prior information. Here, in the context of like a clinical trial, you can call it your base rate. If it's a specific sort of proportion, you can call it a base rate. So let's actually, so this is actually a problem that, oh, well, I should actually ask, now given this information, who thinks that the combination of these numbers would provide a prediction? So again, you know that the base rate of cancer in the population is 10% for that particular type of cancer. And these other two numbers, somebody comes to you with a positive test. Who thinks that the likelihood that they have cancer is above 50? Who thinks the likelihood that they have cancer is above 40? Who think that it's above 30? Who thinks that it's above 20? Starting to get one hand. Who thinks that it's above 10? Who? Okay. So if the test had any accuracy at all, it should be above 10. Like it should inch up that from your prediction from the base rate. I think some of you just were reluctant to make a guess now. Sorry? Right, exactly. Yeah, well, I haven't shown you how to solve it. I just wanted to get your intuition so far. And doctors are terrible at this. This is something that's there's a subset of psychology in combination with economics called judgment and decision making. It's actually the only field where a psychologist has won a Nobel Prize because but they won a Nobel Prize in economics for it. There's no Nobel Prize for psychology. But Kahneman and Tversky sort of made this field, and this is a classic scenario because humans are not good at doing this problem, remembering to take into account the base rate, but also, even when they have the base rate information, taking it into account properly. I think typically the answer that most physicians will give you, even when you give them this base rate, is that with like those numbers, they'd say, oh, I'd say around 60%. I think that it's about 60% chance that somebody with a positive test actually has the cancer. So, but when you work out the math, it turns out to be only about 23%. So physicians under-rely on the base rate information. If you think of that base rate as sort of like a weighting, a way to sort of have like a starting point and then move away from on the basis of how accurate the test is, the physicians move away from it too far, and they should stick closer to the base rate. But how would we get that number? The best way, in fact, this is the way they are not only teaching doctors to do it, but teaching doctors to communicate to their patients about it, is to think of these in terms of hard numbers. So let's imagine, so we've got a base rate of 10%, false negative of 20%, and a false positive of 30%. Let's actually think of 100 individuals being tested, and we know 10 of which have cancer, 90 don't. So the 20% false negative rate means that 10 of those with cancer, of the 10 with cancer, 8 will have positive results and 2 will have a negative result. And of the 30%, the 30% false positive rate means that of the 90 without cancer, 63 will have negative results and 27 will have a false positive. So this gives us sort of the numbers of all the different groups, people who have a positive and accurately get a positive, people that have a positive but are actually, sorry, go ahead.
I'm finding it difficult to understand false negative and false positive.
Oh, okay, so positive means that the test says you have cancer. False part means that you actually don't. So false negative means the test said you don't have cancer, but you actually do. False positive is the test said you have cancer, but you actually don't. So of the 10 people with cancer, 2 were told they don't have cancer. 8 were told, yes, you do have cancer. Of the 90 that don't have cancer, 63 were told, no, you don't have cancer accurately. But 27 were told, yes, you do have cancer. So in order to figure out what the probability of a given person coming to you has cancer, you can just combine these numbers. So you take the 8 true positives, so the people that actually got a positive result and they are positive, and you compare that to the 27 people that got a positive result but they don't actually have cancer. So you combine them, that's 35 people in total had positive results, 8 of which actually have cancer. So 8 divided by 35, that comes out to about 0.23. Without the base rate, you couldn't have established what the size of these 2 groups were. So
with this rest, how did you calculate all these numbers?
Well, you just imagined. So think of 100 individuals. If you know the base rate is 10%, you can immediately say, okay, 10 of them have cancer and 90 don't. And then you can look at that false negative. So that false negative refers to the 10 that have cancer. So
False negative refers
you
to
get,
like 20 patient whose result is
well, 20% of the 10 people. So of the 10 people with cancer, 2 of them, 20% of them, will be given a label that you don't have cancer. And the 30% false positive rate means that of the 90 people we decided don't have cancer, given the base rate, 30% will actually have a positive result, but it's not accurate. So this is a scenario that demonstrates, well, first of all, that if you have a low base rate condition, you want a test, particularly a screening test, that has a really low false positive rate, because the fact, even if you've got like a 95% accuracy in or like an only 5% false positive rate, if you had a really low base rate, you're going to get lots of false positives in the population just because there's so many more people that don't have the disease in the first place. This is why they've started reducing the amount of, say, screening tests in a lot of cancer, prostate cancer, breast cancer, because there are harms associated with false positive. First of all, the stress of thinking that you have cancer. Often there's interventions that are done, so biopsies and things like that, that have their own risks associated with them, that once people have worked out the math on those risks plus just the base rates, have realized, oh, we don't have good enough tools to be asking the question with these tests, so we shouldn't bother. Oh, you had a question?
Yes, a big question. Big one.
Big one, yeah.
So you said that in the beginning, like 80% of the test, if the test comes back positive, it's 80% accurate. Right?
No, I said of those people with cancer, it was 80% accurate at labeling them as having cancer.
But is that positive predictive value or that's the sensitivity? Because
I always get those words confused.
That switched the whole thing.
it is sensitive.
Yes.
Sensitivity, not the possibility.
Okay, yeah. I always get those
You
words.
need to have the real number. Like for the 100 patients, so you have to have true positive, true false positive, then divided by the whole number. But he's talking about the sensitivity and specificity.
Yes, I think so.
Yes, sensitivity and
Yeah.
Because this positive predictive value is the ability of the test to detect disease. And sensitivity is the ability of the test to screen for the disease.
as per I remember, like not the ability, but to tell you like how many patients will have the positive results, the positive prediction.
If you think of a 2x2
Yes.
sort of graph,
Yeah.
I forget the names of these things: sensitivity, specificity, positive predictive value, etc. These numbers correspond to sort of a number that's in a box, not a comparison of the boxes, not any of the sort of ratios or anything like that. These are just the numbers that are in the boxes. So I think sensitivity and specificity, you're right, refer to specific numbers in the
But
boxes.
even the positive and negative, because they are the one at the side.
Yeah, so
The second question is, if you look at the false negative, that means the people who don't have the disease are falsely negative. So to me, 20% of false negative, that means out of the 90, there's a 20% out of the 90 that are actually, they have the disease. Because it's a false negative.
okay, so the false part means whether it was labeled accurately, and
Yes.
negative is what the label was.
Yes.
So 20% false negative means that
People have disease, but they are not detected.
yeah.
So people who don't have the disease are the 90. So 90.
No. You just said people who have disease but aren't detected. So we're not going to refer to them. So if you want to talk about the people who have disease and are not detected, we need to only look at those people with disease, so the 10. So 2 of those 10.
Yeah, 2 of them is not okay. And then
So 65 people are told you do not have cancer.
63-ish, yeah.
Well, no, and 2.
Ah, yes,
So
65
are
total.
told you don't have cancer.
Yeah.
35 are told you do have cancer.
Well, actually, yeah. Yeah, in terms of just the raw tally of who gets a positive and who gets a negative,
So not
yes,
all
2
positives,
plus
positive,
63 will get negative results, and 8 plus 27 will get positive results.
They are not told.
They're not told. The results come
Yeah,
back
yeah,
positive.
yeah,
Fair enough.
yeah.
Okay.
All right, so I mean, this not only was demonstrating, well, a common clinical scenario that clinicians and humans just do poorly at, thinking of the numbers. Converting them to actual numbers is a known sort of way to figure that out a little bit better. But it also demonstrates the general idea that when you're doing any sort of decision about evidence coming in, you need background information on what you would have expected in the first place. So you get this new piece of evidence, a positive result. You have some information about sort of how accurate that information, how sort of uncertain that information is on its own. But then you also have this background information about what to expect without this new data, what you thought, what you would have predicted blindly without seeing that new information. So having seated your minds there to think about that, I'm going to let that stew a little bit. We'll come back to it because we're going to immediately jump to what you guys maybe have already been exposed to in terms of statistics. So this is some histogram data. I broke my rule by only showing one binning size, but we'll accept that. And we're talking about height. You can't see the thing at the bottom, but it's height. So these are the heights of 2 groups, men and women. Men are in pink, blue. Women are in blue. And what would you kind of say about these data if you saw this coming in? Would this... Sorry? The curves are in the wrong place? Well, no, men are pink, women are blue. Or are you saying the curves are miscolored? Well, that depends on your cultural background. Certainly in Western society, we have women associated with, or in modern times actually, it used to be that pink was considered a masculine color and blue was considered a feminine color. That switched. I can't remember the timelines though. I'm thinking it's going back to like 18 or 1700s that color mapping was switched from when it was now. But I'm rather uncertain about my timeline there. But I know it has switched across recorded human history. All right, so this actually just happened to be the default coloring that came out of ggplot. So what can we notice? So you actually seem to have some prior ideas about what heights should be what, because you thought that well, I guess you just thought the labels were switched. Yeah. Okay. So. Okay. So I mean, and you the human visual system is able to just sort of look at that and kind of get information out of it spectacularly. Your brains are doing some neat statistics, but what do you think you're basing that on?
Majority of the
height. Sorry, yeah, height on the x-axis.
in majority, the men are taller than women, but in some small groups, we have women are taller than men.
Okay, so there's some overlap between the 2 distributions there.
It looks like a bell curve, both of them.
Okay, that's another good observation, is that within each group, you've got sort of a kind of a peaked shape, some sort of peaked shape. Yeah. So traditional methods would look at this data, and you might have a question that you want to answer. And if I measured the entire population of men and women all simultaneously for each sex, would I find that these populations are different? That might be a question you have about this data. But before you answer this data, you would have to answer the question different how. So you need to describe on some sort of descriptive characteristic. One might be sort of the general placement of those two distributions. So the arithmetic mean is a measure of location of those distributions. You can think of it actually, if you were to actually literally get a bunch of wooden blocks and put them on a line, the arithmetic mean happens to be the place where if you were to try to balance that on your finger, that's where you would want to put your finger to balance the box. And your eye kind of does that automatically. It finds that point where it sort of geometrically balances things if you were to try to hold it. So the arithmetic mean is sort of a natural thing to use. Despite this being a stats class, we're not going to talk about how that's calculated because it's actually not pertinent for right now. It's just sort of a measure of location is all you need to know. So given that choice of using the arithmetic mean to talk about these two different populations, again, we want to ask the question, if I measure the entire population for each sex, would I find that they have different means? Another way of phrasing that is, if I measure the entire population for each sex, would I find that the difference between their means is 0? Exactly the same, just talking about a difference instead of each individual mean. And so it's hard to answer this question without going out and doing a lot of measurement. Like, we don't have time to measure everybody. And if you, there's ways to approximate going out and doing all that measurement use some computational tools that weren't available to sort of early statisticians. They decided they wanted to change the question. So again, we had this question, if I measure the entire population, would I find that they had different means? So they decided we can't answer that question. We're going to find a different question that we can answer and try to use that instead. So the different question that is being asked by all traditional methods that you're using even now is this one. In a hypothetical world with no difference between the sexes' heights, if I repeated this experiment many times, what proportion of the time would I obtain the difference between the observed means that is as great or greater than the difference I observed in my real experiment? So that's probably not super familiar wording to you guys. It's got lots of clauses associated with them. So again, in a hypothetical world with no difference between the sexes. So you immediately are going to be talking, any sort of result we get from this is going to be a result concerning an imaginary world. We're going to try to connect that imaginary world, or what we have decided about that imaginary world, to what we should decide about the real world, but not yet. So we think about this imaginary world where there's no difference between the sexes. And you imagine, in this imaginary world, repeating your experiment many times. So each time you go out, you measure the same number of men and women that you did in your actual real-world experiment, and you get the mean for those those imaginary experiment groups, and you compute a difference between those imaginary experiment groups. So this should yield a a distribution of imaginary group differences. If you were, again, to somehow get a method to enter an imaginary world and do this. What proportion of the time? So we're going to be talking about proportions here. So we have this distribution of imaginary differences, and we're going to ask about sort of areas of that distribution corresponding to proportions of experiments. Would I obtain a difference between the observed means? That is, so we're going to talk about, again, in each of those experiments, we're getting each of those imaginary experiments, we're getting an imagined difference between groups, and looking at that is as great or greater. So looking at the size of that imagined difference between groups. than the one I observed in my real experiment. So you actually did an experiment and you have this difference between groups out here. And you have this distribution of imagined differences between groups. And you want to know where your difference between groups lies in that distribution of imaginary differences between groups. We still haven't talked about like how you do this imagining and what sort of constraints you might put on your imaginings. But in general, because we've got this proportion of the time, that bit after the proportion of the time is abbreviated as p-value. So that's what your p-value actually is. It's the proportion of the time in a hypothetical world of imagined experiments that you would observe a difference as great or greater than the thing you had in your real experiment. So I haven't told you anything about, did you have a question so far?
That have no difference. How are we gonna find the difference?
Well, just by random chance, every time you sit, if you've got a true, if imaginary world where there really is no difference, but you're doing a sample of the population, each of those samples is going to be randomly just a little bit different from the true population of zero difference. So you might observe, say, 1 centimeter in where one scenario, one imagined world in which your sample has a 1 centimeter male height greater than female height, and another one, females are 2 centimeters greater than males, and another one where it's 0.3 in favor of males, and like they'll generally distribute around zero, and the peak of that distribution of imagined experiments is going to have a peak of around zero, but it's going to, depending on what we decide on how variable the imagined world is, we'll get sort of a spread around zero. But we haven't talked about how we're going to constrain these imaginations, because I can imagine crazy things. So, 1908, William Gossett, working for Guinness Brewing Company, but writing under the name Student Tea so that competing brewing companies wouldn't realize that Guinness was using stats to refine its brewing methods, published the answer, which is if you assume the population has a Gaussian shape, Gaussian being just that certain bell curve that you guys are very familiar with. There's actually a mathematical formula specifying, like, as you go along the x-axis, what the y-axis should be. But assuming the population has this Gaussian shape, and you estimate the variability of the population from the data, so it's the sort of the spread of that bell, you can use an arithmetic formula to derive the p-value. So again, if you have data, you ignore any difference between the data, but you use the variability of the data that you observe to sort of estimate the variability of the population. And then you can use that estimate of variability, combine it with an imaginary world of no difference, and ask about where your observed difference would fall in the distribution of imaginary differences. So there is a solution, and then lots of stuff built on after this. So you get Fisher and his F-test, which is effectively the t-test with the extension that you can start doing things like ANOVA to talk about multiple groups and all. Like, is the variability of these multiple groups consistent with a single group with no difference between the groups, that sort of thing. But before I bother even going into more on, like, okay, how you would actually apply this traditional method and answer that Gossett came up with, since the p-value is an answer to a question we didn't actually intend to ask. Remember, we had this question of, if I were to do this to the real population many times, what would I sort of decide? But the p-value is something pertaining to this imaginary world. What are we going to do with the p-value afterwards? So there's two schools of thought with what you do with a p-value. So Fisher, Ronald Fisher, Sir Ronald Fisher, one of the first sort of eminent statisticians to really think about this, is his argument was to treat it as a measure of strength of evidence. So by this measure, if you had a scenario where your observed difference was far larger than the vast majority of imagined differences. That's kind of like saying, if I were in that imaginary world and I saw this value that we know happens to come from the real world, I'd disbelieve that value. Like I would say that I would think that that value is unlikely to have come from this distribution that is in my imaginary world of zero difference. So you can use the p-value, the sort of proportion of values sort of beyond which the observed value is greater than, as a measure of the strength of evidence. This ends up not really working out because what he's trying to assert here is that a strength of evidence is, when we think of evidence, we're usually talking about how you should think about hypotheses, like what evidence for a hypothesis or against a hypothesis. But the p-value, another way of writing, I don't have my cursor, no, okay. So again, I said the p-value was the sort of representation of sort of the placement in the distribution of imagined differences that our observed difference has in the imaginary world. So another way of expressing that in sort of math, I guess the logic syntax is the probability that the p-value is the probability of the data given the null. That's data given the null is the same as saying we're going to imagine a world in which the null is true, and now we're going to see where in that distribution our actual data value falls, our real world value falls. And it's critically important that that sort of value, probability of data given null, is not equal to the probability of the null given the data. So if I had like a p-value of 0.04, that means that in this imaginary world of the null, data like we actually observed is only occurs in 4% of the sort of experiments that we imagined. That's not saying that the null is only 4% likely to be true. That's a completely different quantity. Because when we say the null is only 4% likely to be true, we're now talking about the real world and the probability of the null given the data. So you can't really treat the p-value as a measure of strength of evidence because we're not really interested in evidence for or against the alternative we're usually interested in the evidence regarding our hypotheses. We're not interested in the probability of the data given some thing about the null. And critically, if you actually use proper metrics of evidence, the relation to the p-value is nonlinear. So there are actual metrics of evidence out there, but p-value doesn't sort of correlate well with it. They correlate and then monotonically, but it's a nonlinear thing. So that's Fisher's perspective. Use it as a measure of strength of evidence. Not really satisfactory. The alternative perspective is Neyman Pearson. And they suggest that you use the p-value to apply a decision rule. So they take the perspective that you're going to be doing a lot of experiments across your career, and you should make a decision in each experiment, or you want to make a decision in each experiment whether your hypothesis is supported or not. So if in each of the experiments that you conduct across your career, you need to choose between the null and the alternative, there are two types of errors that you can make. This should be very familiar because we're talking about, this is almost sort of the diagnostic world. So there are false positives when you choose the alternative when the null is true, and false negatives when you choose the null when the alternative is true. So in sort of parlance of what you guys might be useful, false positives is when you say that you've got a significant result when it actually, like, reality is that that effect isn't there. And false negatives is when you don't obtain a significant result, and reality is that there is a true effect there. You just didn't happen to see it in your experiment. So with Neyman Pearson, you're treating the data in a very much binary fashion. So that actually came out in some of the answers, that you sort of choose a criterion ahead of time. I will suggest that you ignore some of the modern wording I've seen in some stats textbooks saying that if you get a p-value greater than 0.05, you fail to reject, but that somehow implies that you're still not making a decision now. You're just failing to make by failing to reject, if you were to reject, then that's a decision. But if you fail to reject, you're still being wobbly on whether the thing is true. That's nonsensical. The people that suggest that they're philosophically misguided. So you're really in each experiment, you're making a decision. You're choosing the null or you're choosing the alternative. So again, within the Neyman-Pearson decision framework, they concentrate on the rate at which you're committing the errors of the false positive type, saying that there is an effect when there actually isn't out there. And they achieve this by applying a strict procedure to the experiment. So you compute the p-value, so the position in that imaginary distribution where your real data falls. And then you decide to choose the null if the real data falls at a point where only 5% of, or some value alpha percent of the imagined data are greater than or equal to that point. And you choose the alternative if the p-value is, do I have that? Sorry, you choose the null if the value is greater than alpha, so if it's less than that critical value, and you choose the alternative if the p-value is less than or equal to that value. And of course, the value of alpha specifies the acceptable rate of committing false positives, typically set at 0.05. Although in physics it's set at like 0.00001, 6 sigma. So that's it. You are dichotomizing and you're making a decision one way or the other. Whereas with Fisher, you kind of have this continuous metric. You're still computing the p-value, but you're leaving it as is, and you're representing it as a continuous metric of evidence. So the problems with Neyman-Pearson is that, problems with NP and Fisher in general. Okay, well, I elaborated the problems with Fisher in that evidence doesn't, true metrics of evidence don't scale linearly with P, but also it's kind of addressing the wrong probability question. We're interested in probability of our hypotheses given the data. It computes the probability of data in an imaginary world. So problems with NP, Neyman-Pearson, is that, first of all, again, you can have this general question of, in an imaginary world, what would we get? In order to actually make that tractable and do computations given data, you need to start making assumptions. So for example, Gossett started saying, okay, if we think about only interested in the arithmetic mean and we estimate the standard deviation from the populations, that those are assumptions that make it then tractable to start using math to achieve that imaginary world. So the assumptions include that we're only ever interested in the mean. Sometimes you might be interested in whether two groups differ in terms of how variable they are, or maybe if one group is not Gaussian, the other is. We have to make the assumption that the variability that we observe in the world, error, is Gaussian. This is a little bit more nuanced. That data are unstratified or singly and simply stratified. We'll actually get into scenarios of what stratified data is in the first place. But stratified data is a scenario that exists in the world that's traditional analytic solutions, computations can't really handle that well. observed variances are relatively equal. So you might remember in your sort of traditional stats exposure that you can do an actual test for whether your variances are equal with a test for homogeneity variance, and there are some corrections to the t-test if your homogeneity variance test comes out as suggesting that you have different variances. But there's the core thing there is that the traditional tools, mathematical tools, make this assumption, and you have to run around trying to fix things if that assumption isn't met. Another one that's actually not super well known, but the framework only works if you predetermine the n, the amount of sort of effort you're going to go to sampling a population before collecting the data. If you collect data, look at it, and decide that on the basis, decide that, oh, it's close to 0.05, but not quite, and then you go out and collect more data, the p-value changes its meaning. In fact, it's guaranteed that if you use that procedure, you collect data and you keep going until you get lower than 0.05, it's guaranteed that you will get a result lower than 0.05. So the key, that sort of implies that 0.05 means nothing. If you can guarantee a result that gets lower than 0.05, so long as you just collect enough data. So you need, for the p to mean what it's supposed to mean, you need to predetermine the n and stop your experiment once you get to that n and publish those results. Unfortunately, first of all, people aren't really taught that in the first place, and the sociology of how science is done is such that people are motivated to get that less than 0.05, so they just say, okay, I'll keep collecting data. So sort of a little bit more mathematically, the analytic solutions are, even when you get to scenarios where you can start to take into account like stratification and things like that, the solutions are fragile. What I mean is that they might take a lot of time to compute and be very reliant on like random things that you put in your data. They don't like unequal groups, so you have to do sort of adjustments for unequal groups when you do various things. They can't handle missing data. So oftentimes if you're doing, say, a general health screener form, maybe the person didn't want to have the pressure cuffs. So they have their heart rate and maybe a blood draw, but they don't have data for their blood pressure. And so there's missing data. If you're trying to use all those measures from a person to predict some outcome, you'd have to toss that person entirely because they're missing those few little data points, or they're missing data points in one of the variables you're measuring. So traditional methods would mean that you'd have to throw out that person, or go to some elaborate lengths to try to infer what that missing data would have been in the first place as sort of a first step, and then put their data with some fake data entry into the data. In any event, multicollinearity is something that traditional methods don't work well with. This is something that is lamentably ignored in a lot of studies where it's sort of more epidemiological, where you aren't really doing an experiment where you're manipulating whether one person gets a treatment or not, but you're measuring a whole bunch of things like weight and height and looking at the effect on, say, mood. But weight and height are two very correlated things, so they can't be used in a prediction of height or of anything else. If you've got sort of in your regression equation something over here which is some outcome and some number of predictors over here, these predictors are not supposed to be correlated with one another. So if you have both weight and height in your predictor set, we know that weight and height are going to be predicted because the taller you are, the more mass you have to have more weight. So a lot of people will include predictors in their regression models that are highly correlated with one another, and that completely undermines the meaning of the p-values, and it can actually switch the signs of some of like the beta weights and things like that if you have that in your data. So the methods we'll talk about will actually be okay with that. Another sort of niche example is when you've got sort of a contingency table. So contingency tables come up when you've got categorical data. So I guess 1 and 0, so dead or not dead is an example. But when you have, well, imagine a study of men and women and outcomes on different, really contingency tables come up when you have counts that fall into different if you've got sort of buckets of outcomes and you're just counting how many people fall in each bucket. If a bucket doesn't have more than 5 people in it, you actually can't include that bucket. The contingency tables don't work for that scenario. So, yeah, had a question there? These are examples where traditional analytic solutions, they don't work. So there are some corrections for unequal groups. There are some ways to try to handle missing data and to handle multicollinearity. Most texts say that if you have less than 5 accounts of less than 5 in a bucket, you just can't use that bucket. So these are ways in which the traditional tools that are taught fall apart in very realistic scenarios. Who knows about the problems of multiple comparisons? Does the phrase multiple comparison mean anything to you guys? All right. Well, in the same way that in a very similar way that I described that you can always get a p-value of less than 0.05 as long as you just keep collecting data. If you have a lot of comparisons to make within a given data set, so you're not going to collect any more data, but you've got lots of variables that you compare 2 groups on. So I collect 2 groups, but I collect tons of health measures on each of the groups. The more sort of measures that you have in your data set to be able to compare the 2 groups on, the higher the chances that just by random chance, one of them is going to come out to being a significant result. So so if I just had a single measure, so height between men and women, that p-value just maintains its meaning as the p-value if I just have that one variable. But if I decide to run a study where I'm computing a comparison, or I'm measuring height, weight, mood, socioeconomic status, a whole bunch of things, and I do a comparison of men and women on each of these, the p-value, and I make the decision that I'm going to sort of publish a paper no matter which one of these comes out as significant. That p-value no longer means means the same as if I did one study where I did height, and another study where I did weight, and another study where I did socioeconomic status. So multiple comparisons is a big thing when you get into more sort of multivariate data scenarios. And there are methods, again, to try to correct for multiple comparisons, but it's a problem that you then have to deal with traditional methods. And finally, researchers just don't know what a p-value means. You guys had some trouble at the outset sort of being confident at least in your understanding of what a p-value means. I'm pretty sure that what I showed you isn't sort of what you had in your mind, and you were like, that's definitely what the p-value means. And researchers generally, there's actually, people have done surveys of researchers asking, what is a p-value, and giving multiple choice answers, and researchers are terrible at knowing what a p-value actually means. They also don't understand the logic of the Neyman Pearson framework. So oftentimes you'll actually get sort of this combination of the Fisherian perspective and the Neyman Pearson perspective. So they'll start talking about things like marginally significant, as if that were in some way philosophically coherent. These are 2 very different perspectives on what to do with the p-value. One is you just treat it as continuous. 0.06, that might be that sort of is reportable. 0.05 reportable. 0.04 reportable. There are just different degrees on this sliding scale. Whereas the Neyman Pearson is you dichotomize. You make a choice. If it's less than 0.0, you sort of at the outset you decide what your sort of personal criterion is for making one type of error. And if the p is less than 0.05, then you call it significant. If it's not, you call it non-significant. People that use this phrase marginally significant for like 0.07 or 0.06 it's as if they're using significant as if they want to like talk about that making a decision, but they haven't met that 0.05, so they're now going to switch to sort of a strength framework in which they're saying, well, it's kind of close to that 0.05. No, that's complete crap. So
I think the majority of people working in the research, maybe in the medical field, are more to make a decision, right?
Yep.
Like this.
Well, I'd say they are. Well, we'll get into that in a moment. They're going to assert a perspective. Certainly, in the way we write our papers, we will try to draw a conclusion and assert a perspective. But as I'll show, well, we'll get there in a moment. Some people talk. The concept of a confidence interval was sort of mentioned at the outset. Confidence intervals, all the problems that apply to p-values apply to confidence intervals. They're using the exact same math. Confidence intervals are actually yet another weird thing where, so a p-value again, you create this imaginary world, and then you try to talk about where your data might fall in the distribution of results from an imaginary world. Confidence intervals try to say, again, in an imaginary world, if I were to repeat this procedure many times, I would yield a distribution of intervals that are guaranteed to contain the true mean that proportion of the time. But again, that's only in this imaginary world. I can't speak to whether in the real world my interval, what the probability is that my interval actually contains the true mean that exists in the real world. So again, it's a scenario of thinking about something happening in the real world or wanting to talk about the real world, but the math that you're doing is pertaining to an imaginary world. So all the...
Some people claim that p-value is the opposite of confidence interval, which means like this is, you are talking about probability of 5%.
Well, yeah.
Probability of 9.
So this gets into, so there's actually been a trend, at least in my field, away from p-values more towards confidence intervals, as if that solves some of the issues that people have raised about p-values. It solves some of them in the sense that the Neyman-Pearson decision framework for talking about things doesn't really cohere with our perspective of science as sort of like an accumulation of evidence. We're not trying to make one-off decisions. So a confidence interval sort of establishes a better representation of, establishes a representation of uncertainty on something, which is better than just a sort of a point estimate of the rate of something in an imaginary world. But it's still uncertainty about something in an imaginary world, so it's a little bit better. It's moving in the right direction, but I think the people that are really espousing confidence intervals to replace p-values just don't know enough about the other alternatives that are out there that we'll talk about momentarily. And indeed, again, in the same way that there's been sort of survey studies of researchers and multiple choice questions, what does a p-value mean? They've done the same thing with confidence intervals, and researchers are even worse at accurately identifying what a confidence interval means. So, but again, the biggest problem with traditional methods is that they don't ask the questions that we want to ask. So we don't want to control the rate at which we make one of two possible decision types across, or types of decision errors across our careers, as Neyman-Pearson proposes. Science is supposed to be a cumulative endeavor, not a series of one-off decisions. So you might, in your sort of discussion in a section on a paper, you might try to assert a decision for clinical scenarios where a physician has somebody in front of them and they need to make a decision, put them on a drug or not. So there are scenarios where you have to make recommendations. But when you're actually doing the statistical part of things, where you're just trying to represent the information from your data, I would suggest you're not trying to make decisions at that stage. And we don't want to talk about the probability of the data given the null, as Fisher proposes as sort of his metric of evidence. We're much more interested in talking about the credibility of various hypotheses, the null, some alternative hypotheses, given the data. So this brings us to the Bayesian approach. So the Bayesian approach asks the question that we actually have wanted to answer. It asks, what do the data say with regards to what I should believe? Another way of phrasing that is, what do the data say with regards to how I should believe in any given hypothesis relative to any other hypothesis out there? So if I have multiple hypotheses, how much should I believe in this one versus this one? Like, what do the data say with regards to which one I should believe more? You could ask, so I want to know, how credible is a difference of 0? How credible is a difference of 1 centimeter in the case of like a scenario of heights? So how credible is a true difference in the world of different heights between men and women of 1 centimeter? How credible is a difference of 2 centimeters, etc.?
When you're saying difference, do you mean difference between means?
Yeah. So again, you are going to operationalize what thing you're measuring and comparing. The Bayesian approach will allow you to compare many more metrics, though. We'll get into that. And one key to the Bayesian approach is that in determining the credibility of a given hypothesis, you need to include all the information at your disposal. And in the same way that we eventually realized that we needed the base rate of a disease in a population before we could speak to what we should believe given a positive result. We not only have to deal with the sort of new data at hand, but any other prior data we might have sort of gathered in our experience. So again, that base rate represents sort of prior data that you would have gathered before even seeing this person coming in with their data of a positive result. So if there is prior data available, so if you have like the original sample that the base rate was estimated from, you can use that in your statistics. But if the prior data isn't available, you can use there's a way to represent your beliefs mathematically because we all have sort of beliefs. You would have not believed a difference. If I tried to tell you what is your, before seeing any height data, what would your credibility be that men are a meter taller than women on average? You would not believe me very much, because you all have an experience with men and women that's sort of being haphazard and somewhat subjective, but 100, I'm pretty sure most of you would reject as a credible hypothesis. Maybe 8 centimeters, that might be a more credible hypothesis. You're going to start being more varied from one to another as to how credible they are, the closer we get to sort of a real representation. But there are ways to reflect your beliefs mathematically, and we'll get into doing that in a way that you then can represent those beliefs to others. So let's remember the quiz. We've got the false positive rate of 30%. False negative rate of 20%. The reason why this is called the Bayesian approach is because if you had a scenario like this where you have the rate of these two types of events and then the base rate, the person that figured out the math for combining these without doing the the count representation, just doing it on the probabilities, it was a guy. The Reverend Bayes. What was his first name? Thomas Bayes. Yes, I think so. So things you need to compute are for the Bayesian formula. There's a mathematical formula. You won't need to know it. For your interest, I'm going to show you here. You need to have the first three pieces of information, you can derive the fourth piece of information, positive rate. That's the rate of everybody regard. So that's the rate of that we actually talked about earlier, that 35 people in that case of 100 would have a positive test result. So you can combine those first three to determine what proportion of people will have a positive test result, regardless of whether they are positive or not. So you can call that the positive rate. So the Bayesian formula, or Bayes' rule, is whenever you have a hypothesis and data, and you want to know what is the probability of my hypothesis given a new set of data, you need these three pieces of information. The probability of the hypothesis, so that's like your prior. So the hypothesis is this person has cancer. Data is the positive result. So P hypothesis is the probability that this person has cancer, regardless of any data out there. So not any data out there, but before you saw the current data. So that's your prior. PH is your prior. You combine that with the probability of data given the hypothesis. So that's actually very similar to the p-value that we saw before, in that it's the probability of data given some hypothesis. Here it's a little different because we're going to talk solely about the hypothesis that we are interested in inferring about. So probability of data given the hypothesis, that is the scenario where you look at, if our hypothesis is people have cancer, you're looking at what is the proportion of people that have cancer that get a positive result. That's that P data given hypothesis. And you divide and you combine that with that overall positive rate. That's P data. Data again being a positive result. So applied to our quiz, the probability of having cancer given a positive test result is the combination of the probability of having cancer times the probability of having a positive result divided by, given that you have cancer, divided by the probability of just having a positive result regardless of whether you have cancer or not. So in the same way that we actually just figured out like some numbers and counts of things, this is what we were doing sort of in the background when we were doing those counts, is we were computing out what those things were. So 0.1 times 0.8 divided by 0.35 ends up having that same number that we got out in the first place, about 0.23. Obviously a lot easier to do it with the count, and humans are better at understanding it with the count. But this is where Bayes' rule comes from in general. You're not going to need to actually work this out yourselves ever. This applies, the Bayes rule applies when you have point estimates for each of these things. So particularly, I told you the base rate of cancer in the population was 10%. But how did I get that number? Maybe I measured the entire population and was able to figure out definitively that only 10% of people. Well, if I did that, I wouldn't need a diagnostic test. So presumably that came from some prior study that hopefully looked at a lot of people with some super accurate gold standard and was able to establish that the prevalence rate was 10%. But there's probably some uncertainty associated with that 10%. Maybe I believe 10% as the most credible value for the true rate in the population. But maybe I definitely wouldn't believe 1%, and maybe I wouldn't believe 20%. So I'd sort of assign those low credibility, but I'd be pretty credible of 12% and 8%. So you can imagine sort of a distribution peaked at 10%, peaked at where sort of our estimate from the prior literature would be, but sort of tapering off to the side so that we wouldn't believe, say, 100%, or definitely wouldn't believe 0%. So some sort of distribution of beliefs. If you have that scenario, well, how do we sort of replace that 0.1 with a distribution? And this is where I'm not going to tell you guys. We're going to use a black box to do it automatically for us. So actually, I think I do have an example. How much time? 12:55. Oh, we only, yeah, no, it's time for class to be done. So we'll go a little bit more into this next class, and hopefully you're excited to get away from a demonstrably bad way of doing stats to, I haven't told you, yeah, we'll continue this lecture actually, and in addition to being more philosophically grounded, there's a whole lot of sort of cool stuff that the Bayesian approach can do. It's much more flexible. You can talk about many more properties of data, not just the mean. It can handle different types of data, missing data, all those things that I talked about the traditional framework being fragile with or having troubles with. The Bayesian approach is the opposite of that. So